All right, we've learned that the derivative of a function can be considered a function itself, but we haven't actually calculated any of them yet. So I want to do our first one now. If f of x equals x cubed, find a formula for f prime of x, then compare the graphs of f and f prime. So we want to find the derivative f prime of x, and we know that this comes from the limit as h approaches 0 of f of x plus h minus f of x all over h. So we need to plug in these things with our function f of x equals x cubed. So this is going to be the limit as h approaches 0 of, our function is the cubing function, so f of x plus h is going to be x plus h cubed, minus f of x is x cubed all over h. All right. So we have to expand x plus h cubed. And I don't want to go through and write out every single step here, but I'm going to do a little bit of a skeleton sort of a framework for this problem, because I know that some students might not have the strong algebra background to do this. So x plus h cubed is going to be x plus h times x plus h squared, and x plus h squared is x squared plus 2xh plus h squared. All right. And then if we want to multiply those out, there's different ways of doing this. I like to do a thing called the box method, or the table method, where I set up a table and we're putting each of the product terms in individual boxes. If you are comfortable with this and know how to do this, you can skip ahead in this part of the video. But so in the first box here, we've got x times x squared is x cubed. In the next one, we've got x times 2xh, and that's going to be 2x squared h. And then we've got x times h squared, that's xh squared. And then in the next row, x squared times h is x squared h. And then 2xh times h is 2xh squared. And then we've got h cubed in the bottom. And then we can combine like terms. We've got x squared h terms there, and we've got xh squared terms there. And when we go through and combine like terms, this is going to leave us with x cubed plus 3x squared h plus 3xh squared plus h cubed. And then we're still subtracting x cubed, so we've got minus x cubed, and this is all over h. Now there's just a little bit of canceling we can do. We've got a positive x cubed and a negative x cubed. We can cancel those out. Those go away. And then if we look at all the remaining terms, they all have an h in them. So we can actually go through and divide out that h from the denominator. All right, 3x squared h divided by h is going to be 3x squared plus 3xh squared divided by h is going to be 3xh. And then that h cubed divided by h is h squared. And now that we've gotten rid of the h in the denominator, we've got a polynomial here. We can use direct substitution and plug in h equals 0. That's going to make these last two terms go away. And so all we're going to have left is 3x squared. So that means that the derivative of the function f of x equals x cubed is the function 3x squared. Now, if we want to compare these graphs, I'm going to do a rough sketch here. We know that the graph of f of x equals x cubed looks something like this. It goes very steeply up to the right and very steeply down to the left, except it's a little flat in the middle, less steep there. That is our function, f of x equals x cubed. Now, our derivative is 3x squared. We know that this is a parabola. I don't know exactly how steep they are compared to each other. I'm going to draw them like this. This is just a rough sketch. If we wanted to, we could take all the time in the world and we could really make a table of values and everything and do a big comparison, but I don't want this video to be 12 minutes long. What I really want to look at is I want to compare these graphs. On the right-hand side, if you look at our function, the function is increasing. At first, just a little bit, but then more and more steeply. That means the derivative is going to be positive because the function is increasing. And because it's getting steeper, that means the slopes of the tangent lines are going to get bigger, which means the derivative is going to get bigger. So that's why we can see that it's increasing as we go from left to right. Now, our function has a horizontal tangent line at 0. That means the slope of the tangent line is going to be 0 there, which means the derivative is 0. And then if we look at our function on the left-hand side, it still is increasing from left to right. That means that all of the tangent lines are going to have positive slope, and that's why the function, again, is above the x-axis, because the derivative is going to be positive here. And we can see that as we move to the left, the steepness is increasing, and that's why the derivative, as we move to the left, is increasing as well. So that's really a rough comparison of those two graphs, the function itself and the derivative.